Welcome. Today's lesson is entitled Exponential Growth and Decay Models, Day 1. And today's lesson and tomorrow's lesson offer us just an opportunity to do some applications with exponential growth and decay. And so we'll start that process working a little bit with the number e. So let's go ahead and take a look at what's on your paper there. The investigation is the number e, and we kind of saw the number e within the context, of compound interest. And we'll go ahead and relate that to compound interest in just a little bit. But let's just do a little number crunching to kind of see this number in action. So it just says on your paper, evaluate the expression. And look at that right there. Should look vaguely familiar. Has a little context, a little background for us. So evaluate that expression for each n value to 9 decimal places. And that would be the limit on our calculator when appropriate. So what we're going to do is allow n to get infinitely large. We're going to get larger and larger and larger. And what I want to know is what happens to the value of this expression right here. So you can kind of see, I tried to streamline this a little bit for us, starting out really small and then jumping up in a hurry. So starting out with a small n value of 1, and by the end of this, we'll get all the way up to 100 million. And what I want to know is what happens to the value of that expression. So let's go for it. I'm going to grab my calculator. If you could do the same, please, and do this with me. So nice and easy, just exactly as it's on your paper there. Left parenthesis, 1 plus 1 divided by, n is going to be 1. And we're going to raise that to the first. And this shouldn't come as a shocker, but that, of course, would be 2. All right, so let's get a 2 right in there. That's looking good. Now what happens when we do 100? So in this case, this 1 is going to be divided 100 times and then raised to the 100th. So I don't want to give too much away in terms of explaining these values, but let's let n be 100 initially here. Raise it to 100. So what obviously is happening, I guess numerically, is we're getting smaller and smaller numbers in here. Instead of 1 over 1, we're getting 1 over 100. So smaller in here, but raising it to larger powers. And when we do that, notice you get something a little larger than the 2. And I've got it on my paper here, so I'm going to write the whole thing out. So it looks like 2.704813829. Very nice. All right, let's jump it up. A couple factors of 10. So from 100 to 10,000. Here we go. Come on. So left parenthesis, 1 plus. Now again, it's getting smaller inside. Instead of 1 plus this, it's 1 plus 1 over 10,000. But even though it's getting smaller inside, I'm going to raise it to a larger number outside. And take a look at what we get there. In the range. So it's 2.718. I've got 145927 on my paper. So just make sure that matches. All right, let's bump it up a couple more times here. Another couple factors of 10. So from 10,000 all the way up to 1,000,000. What would happen? Let's see. Go for it, guys. Come on, left parenthesis. Don't shortchange it. Really small inside, so now it's 1 over 1,000,000. So let me make sure I've got enough zeros there. Good. And then raise it. Same deal. And let's see. Look at that. Notice starting to have to go pretty far back just to see the change, right? Does that idea sound familiar? Oh, it should. We did this before. So if it was 1,000,000, I got 2.718280469. All right, great. Let's do it one more time, guys. Bump it up by another couple factors of 10. So from 1,000,000 all the way up to 100 mil. Here we go, last time. So parentheses, 1 plus 1 divided by 100 million. Okay, close that off, raise it to, same deal, 100 million. Hope I have my zeros right. We'll find out. Yeah, it looks pretty good. Okay, so as you can see, look at the last 2 entries. Look how far back we have to go. 1, 2, 3, 4, 5. I have to go 6 decimal places back just to see it, even though our n value increased by 99 million. Holy cow. And we had to go so far back just to see any change whatsoever. So I got, what was that, 18281815, something like that. Again, everyone, could I theoretically keep going? Could I start getting into the billions and the trillions, et cetera, et cetera? And I guess the question sort of speaks for itself. Is there a limit to your answers, or are your answers increasing without bound? And, you know, I guess you could argue there is a limit. No doubt about it. These seem to be leveling off towards a particular number. I hope everybody is in agreement with that piece. What they are leveling off towards is E. So as n gets infinitely large, the values of this expression, here we go guys, approach the number E. And so one definition of E, and if you could kind of highlight this piece or box that up, that would be ideal. So one definition, there are a couple others out there. You could do a little research and explore them. There are some interesting ways to get E, but this is probably the most common. We would read this as the limit as n approaches infinity, so n gets infinitely large, of this expression right here. And that's exactly what we did. We got up to about 100 million, but again, that's really just the tip of the iceberg. We can keep going and going and going, and as n gets infinitely large, you can see that our values approach the number E. Now, it's going to sound a little simplistic, but can I put infinity into this expression? No. So can I actually calculate the number E as something tangible and rational? No. And that's why E is what is called an irrational number, very much along the lines of pi. Very, very cool. Let's explore just a little further. Let's get E on the calculator there. A couple ways to get E on the calculator. I'm going to do just the button we've done all along, kind of that E raised to, because mostly E is used as the base to an exponential function, and the calculator knows that, so that's why it's being raised off right away. So let's just do E to the first. And you can see, look at that compared to kind of our last entry. So this is your calculator rounding to 9 decimal places of what E is, and notice it's just a touch larger than that right there. So I'm going to go ahead and write that. So it's 2.718281828. Now it's kind of interesting. I had said this is an irrational number, and it is. An irrational number, by definition, is represented as a decimal that never terminates and never repeats. And so that's actually the case here. I know you see a little repeat, 18281828, but it doesn't continue that. That pattern does not continue. So this is to 9 decimal places, but theoretically, you know, there's a little dot, dot, dot on this, and it goes on infinitely. Cool. Now here's, to me, the great thing. Let's see if you can really put some meaning behind it. It says, give a verbal description of this, and think compound interest for just a second. Think compound interest, because again, we've done those calculations before. We've seen a very similar pattern to what we just did above. So think compound interest here. And do you remember that good old effective rate? Now don't write this on your paper, but do you remember that effective rate for compound interest, which was basically this? And doesn't it kind of look like that piece right there? In this case, what would the R value be if I just put a 1 right there? What would be the percentage? Well, I'm hoping you would agree that this is really would be 100%, right? So R would be 1, so that's 100%. And we never really talked about the principle out in front, but theoretically when we talk about an effective rate increasing, we talk about it increasing from $1. Think about like a little 1 standing out in front. And what we did, and what we just did here as well, is we let n get infinitely large, and we saw those values level off. Well, a long story short here, this is what I have on my paper, and I think it's a pretty good definition. It is the limit, sorry, let me make sure I get that right for you. It is the limit of the effective rate. And by limit, what we're saying is n is going to infinity, because n is getting larger and larger and larger and larger, but it's approaching a particular value. And the limit of that is E in this case. So it's the limit of the effective rate for $1, here's the $1, growing at 100% annual interest. Kind of cool. And that's an interesting little verbal definition of what E is. The context that it's used in is primarily as the base of an exponential function. With compound interest, we apply it as e to the r in order to get the limit of the effective rate for any nominal rate. All that good stuff that we talked about. But just the number e itself really can be verbally described as this. $1, here it is, $1 right here, growing at 100% interest. And what we would do is let the number of compounding periods approach infinity. And as this number gets higher and higher and higher, the value of this expression, the value of that effective rate, approaches e. Awesome. Very, very cool stuff. Okay, well, let's move forward. Basically, what we're going to explore is the two representations of an exponential model. And so I'm going to box these two up. This is the one that we've done the most work with. This is probably the model that we will use on the next lesson as well. I think there's some great application that goes with y equals a times b to the x. As it so happens, any exponential model can also be written in a uniform base using this irrational number e. These two things mean the exact same thing, just two different forms of expressing a mathematical phenomenon that grows or decays exponentially. Well, let's go ahead and just write some things in and then do the couple examples on the back here. So first of all, really most of it comes down to the b value in my opinion, and we'll see this on the next lesson as well. Most of the applications will revolve around b. So let's go ahead and put that in there. B is really the effective rate. I mean, that's the best way for me to describe it. It is the true growth rate in a time period. So I'm going to write this, growth / decay rate in a time period. And when we started this unit, we talked about exactly that piece. It comes from a percentage increase in a time period, and or decrease for that matter, and we go ahead and we went out and got our b value as a result. So I would call it the effective rate. It's really the true growth rate in a time period. Okay, now this base e, again the notation is a little different, but you'll see it syncs up very nicely. This a sub 0 is really the amount at time 0, or in layman's terms, just the initial quantity. So initial quantity. All right, good. T, of course, is the number of time periods. Okay, no big deal there. The independent variable, typically in terms of time. A, of course, is the dependent variable, and that would be the amount after t time periods. So A depends on t as usual. So in this case, amount after t time periods. Nice. And then K is an interesting little thing. As a measurement, sometimes it's called the continuous growth or decay rate. Again, I won't hold you too accountable for this, so don't worry too much about this piece. Just using the algebra behind it is fine by me. So typically it's called the continuous growth or decay rate. And here's the idea, I guess, just real quick, and then we'll go back to the idea of compound interest. If it's bigger than 0, it happens to be growth. Here's what's kind of cool about it, working in base E. If k is positive, it's growth. And if k is negative, it happens to be decay. So a quick, easy way to tell growth versus decay. And that is different, of course. Let's compare and contrast a little. That's different than the base B model, where if you remember base B, bigger than 1 growth, between 0 and 1 decay. So again, just a little different in that way. Basically, just again, don't read too much into this. Don't get too hung up on this piece. Just think of this as the PERT formula that we worked on with compound interest, just now expanded to quantities other than money. That's all. So this is PERT. Here's your A. This is P, E. This K value is really just that same thing, that R, T. So this is really just PERT. So when we talk about this K value, I sort of thinking about it in just mathematically what it would be is really the rate of increase before being compounded continuously. After it's compounded continuously, we get our effective rate. What would be the limit of that effective rate? All right, enough rambling. Let's get down to the business at hand. So I think I alluded to this. Every exponential model in base B can be written in base E, and every exponential model in base E can be written in base B. Two different ways to represent mathematical phenomenon that increase or decrease exponentially. Now, there's a relationship between the two, and that's what we'll just quickly explore and then do our two problems for the day. So this is the one I do most of my application work around. And again, on tomorrow's notes worksheet, talk just very little about E, but most of it will be y equals a times b to the x. And this is what you will be using, really mostly y equals a times b to the x. But again, it should be noted, especially at this level, that we can also work in base E. And so if you really sort of break it on down, most of this is identical. These two things are absolutely the same. They're the dependent variable. So circle those for me if you would. These two things are identical in nature. They are the independent variable. No big deal. They're different letters, but they mean the same thing. These two things are the same in the initial quantity, what I start with, which means when all said and done, syncing these two up and just figuring out they're two different representations of the same type of growth or decay, then we see that these two are also the same. So our B value is equivalent to e to the k, and that's just the algebra that we'll explore. And we won't do too much with it, but it is something you will be able to work with algebraically, and that's all. This would be the effective rate. This would be the continuous rate. That's all. All right, well, let's give it a try. You know, sometimes it gets a little abstract, and you know, it's sort of the nature of the course. But let's kind of round it out here, do some examples, and just do some number crunching with it. So here we go. The exponential growth of a colony of bacteria can be modeled with the function right there. I'm going to box that up, where n is measured in grams and t is measured in days. What's the population after 5 days? All right, so hey, this is just a nice looking exponential growth model written in our base E. No big deal, because basically if I give you an input, you can come up with an output pretty easily. So in this case, 5 days. Don't overthink, guys. We're just applying a base E model. That's all. Just working with the algebra behind it. And so I'm going to go ahead and bring the calculator up just to go ahead and get this going. And so we started with 80. Again, notice, look, when I hit that button, it knows that we want the exponential function in base E there. So e raised 2, it automatically gets that going. And it also knows that you're going to kind of have your RT in here, because notice it gave you a parenthesis because it knows it wants you to do this and then the e raised 2. So look at that. You know, the calculator has the context for which e is used, and we end up getting something along those lines right there. So I get about 100.19 if we want to round, I guess, because I don't know, in terms of the bacteria here, whatever. I'll go with that. Oh, this is grams, so never mind. I'll go ahead and include the decimals. All right, and there you go. That shouldn't scare us at all. Given an input, come up with the output base E. Let's reverse it. After how long will the population double? So, you know, if we interpret our model correctly, there's the initial population. How long will it take for that to double? So if I start at 80, I'm hoping you're okay with the fact that the 160 is going to come into play right over there. And what I'm looking for is, with this particular type of growth, how many days, because t is measured in days, would it take for the 80 to get up to the 160? And there is an advantage to working in base E, by the way, as you'll see just solving, because I'm going to go ahead and divide right there, and I get my 2, hence the doubling, by the way. And so I'm going to go ahead and solve an equation like that. And that's something we should be pretty comfortable with, because that E is going to just roll on over to the other side. And basically, when it does, I just get the natural log of 2. And so the natural log of 2 equals 0.045t. And look how great that is. Again, no change of base formula required. Again, just this nice uniform base. It has its own button on the calculator. And so when I roll it over, all I have to do is type in ln of 2 right there. Let's divide that by the 0.045. And I'm hoping everyone agrees with exactly that scenario. And there we go. And so I have about 15.4 days when all's said and done. So take a look at that and make sure that makes pretty good sense. Basically all we did is we took that base E and rolled it on over. Remember, it changes to the base of the logarithm when we do that. So there's your log base E right there, the natural logarithm. Cool. Well, as mentioned, just one more piece. This model right here, which was perfectly legitimate to do the work required in this problem, again, theoretically can be modeled in base B, and that's all, just getting comfortable with that piece. So I'm going to write e to the k is equal to b, just like I did above. And notice, in this particular situation, we have e to the k. We have e to the 0.045. And as we've seen before, that is essentially the limit of the effective rate for growing at, we would call this 4.5%. When it's compounded continuously, we get something that should be a little greater than 4.5%. And so we're just going to let the calculator do the work here. So what is e raised to the 0.045? That would officially be our b value in the exponential model. So what do we say? E raised to the 0.045, and I hit enter, and I get that right there. So I just sort of think about this. This is the rate before being compounded continuously. Once you apply that base E, then it has been compounded continuously, and it should be a little bigger, something like that. And I don't know, let's go ahead and write our model then as a result. So the number of grams is equal to that 80, and this is probably what it would look like in base B if I wanted it to, and I maybe cut it off a little too soon, but whatever. This model and the original model are identical mathematically. Great. Very cool. So I gave you the base E model there. You won't have to come up with a base E model, just so you know. What you will have to work with is primarily the base B model. That's what I focused my attention on. As I said, my opinion is that most of the great application comes from working in y equals a times b to the x. So this would be a perfect problem. I mean, this is just as good as it gets in terms of an application dealing with exponential growth and working with y equals a times b to the x. I think it's absolutely superb. So again, you do not have to write your own model in base E. What I would ask us to do is, after we kind of work with a problem in base B, can you at least think about the algebraic connection to base E? Well, let's give it a try. You know, again, population is just probably the most well-known quantity that increases exponentially. So let's go broad here. The world's population in the year 2000, so this is the mid-year estimate, is this right here, just over 6 billion. In 2010, same thing, so exactly 10 years later, we've got that mid-year estimate right there, so getting close to 7 billion. So write an exponential function for the population in that period of time. Everybody, if you would, again, given information, growing exponentially, it's y equals a times b to the x, and this is definitely what you're going to see on the next notes worksheet all the way through. Okay, well, let's go for it. We have an initial population, right? We have an initial value, starting the model in the year 2000. So crazy numbers here, but that's all right. Let's go for it. I do not know how it's growing over that time frame. I do not know that b value. But I'm going to need to find it to write this model. I do know 10 years later that this initial population has grown all the way to close to 7 billion. Let's see if I can get these numbers in, 932,929. So I'm going to go ahead and do a little division on this and then ask you kind of what do you think we should do in order to get our b value there. So let's finish up nice and strong on this one. This is a great problem. So I have, let's see, actually, make sure I've got my numbers correct. So 6,848,932,929. Take that and divide it by 6,082,966 429. All right, I think I've got it. There we go, and perfect. So I get about 1.1259. 1.1259, and that is b to the 10th, which in reality, just for your information, would be the growth rate over 10 years. And if you kind of look at it, if you were to put your hand on that one right there, that would be about 12.59%. So the world's population increased by about 12.59% over that 10-year span. Well, what does that mean in terms of the growth rate per year? Well, potentially we've seen this before. I know you'll definitely see it again, but how do I get that b value if it's being raised to the 10th? No logarithm here, everybody. I'm going to go ahead and apply a 10th root. I don't divide by 10. I apply a 10th root. And when I apply that 10th root on this number right here, that should give me the growth factor each and every year from one year to the next to the next. It's kind of cool. Well, everyone, hit the number 10 on your calculator for me. Go under Math, and it happens to be the number 5 right there, so the x root. And what did we say? 1.1259. And there we have it. So let's see what we have going. I've got 1.01193. So let's see, 1.01193, and that's our growth rate. Wonderful. Which means, again, well, let's write the model first. I'm sorry, I got ahead of myself. And let's see, let's go population in terms of time. So population is, starting it out for this model, 6,082,966,429 times 1.01193 raised to the t. What a great looking model that is. Nice. There is a secondary question quickly to part A, and then we'll get into B and kind of go from there. It says, what is the effective annual growth rate? Really, by what percent did it increase each and every year from one year to the next to the next? The population seems to be increasing by a percentage according to this model. Well, remember, just the b value, and you don't have to write this on your paper if you don't want to, is always 1 plus r if it's growth. So we get 1.01193 equals 1 plus r. So r is 0.01193, which is, there you go. So the first part of the new century, the world's population increased by about 1.2, give or take, about 1.2% per year. Awesome. Look at that. Great. Now, as I alluded to before, every model in base B can be written in base E. So again, don't write this on your paper just yet, but that's all. I'm just going to go ahead and write the exact same model using that uniform base, just understanding that it can be. And it all comes down to this piece right here. So wrote it above. Let's just go to work on it. So that b value, which we got as 1.01193, was e to the k. And in this case, it's not quite as straightforward, but you know, it's something we can solve, and that's all. It's just good algebra. That e would roll on over to the other side, and I'm hoping you would understand that rk is really the natural logarithm of that b value. So I don't know. Let's go ahead and just get that, and then write the model, and just apply it using letter C on your paper. So let's see, natural log. I have 1.01193. Good. And there we go. So you can see k, we can do this for as many decimal places as we'd like. The more the better, but I get 0.011859. So 0.011859, give or take. And that would be the k value. If we were to write that same model, I'm going to go population in terms of time. So we started at 6 bill. And we use our little uniform base, e, for this exponential model. And that e is raised to the 0.011859 times t. Two representations of the same exponential growth. Either one would be legitimate. Again, algebraically, maybe when we solve for letter C here, maybe base E would be better for you. I don't know. Your call. I would love for you to pause the video at this stage and just, your algebra is great at this point of the unit. So we'd love for you to put in 8 billion for the population and solve for a T for me. Either one. You could put it here or in the base B model or the base E model. Your call. All right. Well, I'm hoping you did it. I'm hoping you paused the video and made it happen. I'm going to start the process. Probably have to go a little bit over to the side here, but 8 billion. There you go. Yikes. Nice. Got that. Just want to make sure I'm all covered. 429. And again, I'm going to go base B just because I work in that. I know this is easier in base E. I do want to emphasize that piece. But I just like working in base B so often that, and again, most of the application I think works well in base B. So just as a prelude to tomorrow's lesson, I'm going to go ahead and solve this. So, well, let's go ahead and divide. That's not going to be pleasant, but let's divide, take a logarithm, and I think we'll get our answer. So let me go ahead and come on over here and type in that ridiculously large number and see what we get. So 8 billion divided by the initial part, which was 60, there we go, 966. 429. Hopefully I have all my numbers in, and I get that. All right, not too bad. So 1.3151. 1.3151. Probably shouldn't have, well, I rounded maybe a little too soon, but we'll see. Anyway, I'm going to go ahead and roll that on over to the other side, and T should just be the log base, 1.01193 of 1.3151, etc. I'll let the calculator do a little better than I wrote it right here. Everyone okay with that? Just rolling that on over to the other side. It becomes the base of the logarithm. I have to do a change of base formula. Maybe you can shortchange it a little, but it basically will be log of the input divided by log of the base for me. So I'm going to actually be able to let the calculator do some good stuff with this. So log of the answer divided by log of 1.01193, and we've got a winner. So in about 23.1 years, the population can expect to reach, what did we say, 8 billion. So I'm going to write that, 23.1 years, which of course would be about 2023. Hoping that regardless of which model you used, you got something in that vicinity. Well, again, just some great applications dealing with exponential growth and decay. You'll see more tomorrow, trying to make it as applicable and as relevant as possible as we round out this good unit here. Thanks for listening, of course. If you have questions along the way, don't hesitate to ask. And try some practice with this and work on it a little, see if something piques your interest. Hey, thanks for listening, of course.